My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 495. In this lecture, we will try to understand Dbscan algorithm. Given all of the terms that we learned, let's go into the core of the Dbscan algorithm on how it works. The first step of the algorithm is for each point xi that belongs to your dataset capital D, your first job is to label each point as core point or border point or noise point. When you run Dbscan algorithm, you get two hyperparameters. The first hyperparameter is min points and the second hyperparameter is epsilon. Given these two hyperparameters, we will learn how to determine the right parameters ladder. Given these hyperparameters min points and epsilon, for every point you can find whether it is a core point, border point or noise point, because what you do is a very simple given a point xi, you would see within epsilon radius how many points are there, isn't it? Within epsilon radius, how many points are there? If the number of points are more than min points, you would call it as core point. Each point you have to label as core point. X1 may be core point, X2 may be border point, X3 may be noise point, X4 may be core point, X5 may be core point. And isn't it? Each point you have to label is like this, isn't it? You need to do something called as to label. Each point you have to label. You need to do this. So you need to do something called as a range query, isn't it? What is the range query? Range query basically does this. Given a point xi, it returns all the points within an epsilon radius. Imagine all of this data capital D. You need to be able to say, you can give a range query and say s equal to range query of xi comma capital D comma epsilon. What it should return is it should return a set capital S of points, set Si of points which are within an epsilon range. If you give point xi, dataset capital D and an epsilon radius, this range query should be able to return us all the points which are within epsilon radius. This range query typically implemented using data structures like KD tree, isn't it? For those of you forgotten what is KD tree, we learned KD tree when we learned in Canaan. It uses data structures like KD tree or even we learned data structures like KD tree or octree, which are variations of KD tree. To enable this range queries very efficiently, you can make use of this particular data structure. So the data structure KD tree that we learned in Canaan is also used Dbscan algorithm. Of course, there are other implementations of range queries. Dbscan was created by folks from databases, data mining, and not by core machine learning engineers. In databases, there are special tools that people have built to make range queries very efficiently on data points like this. Internally, they might be using a KD tree. Of course, the first step is very simple. Given each point xi belongs to capital D, I can label it as a core point or noise point. To do this, we need to do range queries. Range queries, you can implement them efficiently. sklearn uses KD tree internally for implementing Dbscan algorithm. The second step is remove all the noise points from your dataset. So for every point you have said whether it is core point, border point or noise point, remove all the noise points from your data, because noise points belongs to sparse regions, which means they don't belongs to any cluster. So they don't belongs to any cluster, and hence we will remove them. The third step is which is the core step, is for each core point P that is not assigned to a cluster, you perform these two steps. First step is to create new cluster with P. Second step is add all the points that are densely connected to P into the new cluster. At the outset, you don't have any points which is assigned to the cluster. None of the core points are assigned, so you pick one of the core points at random, you create a cluster with this core point. Now you say which one points are densely connected, which one points are densely connected. So what is densely connected means? Densely connected means if this is my core point P, let me say, just try to recall, we discussed already this density connect. This is my core point P. If P1 is within an epsilon distance, and it is density connected. Remember, P2 is also density connected with P. If you point P3 here, if your point P3 is here, similarly if you point P4, just say, if this I already discussed in previous lecture, P4 here, P5 is here, and P6, all these points are densely connected. If all these P1 to P6 are core points and the distance between each of them is less than or equal to epsilon. So first take one core point at random initially, look at all the points that are densely connected to P and add them to the cluster, and if there are some more core points, this is a loop. Which one is a loop? This is a loop. This is loop. First we'll execute A, then B. This entire thing is a loop, isn't it? Yes, if there are some core points still left, if there are some core points still left, all this becomes one cluster. All this becomes one cluster. This one will become one cluster. Suppose there is other point P8. Let me say there is other point P8 which is not reachable from P. This P8 is not reachable from P. That is important. This P8 is not reachable from P. In my second iteration, my P8 becomes P. This P8 becomes my second iteration. P8 becomes P, and probably P8 can be reachable from P9. P8 might be reachable from P9, isn't it? P10 and P12, and all of them become next cluster. Therefore, in that case, these points will become another cluster. This is one cluster. This is first cluster. Let me say. This is, let me say, something like second cluster. We remove all the noise points, and all the core points are taken care for. What happens to border points? Take each border point and assign these border points. Assign it to the nearest core point cluster. Suppose if you have a core point, let's call it as PC. PC is my core point. Let's assume there is a border point here, PB. Yes, suppose this is PC belonging to this particular, let me say PC belongs to this particular cluster. PB is a border point, and nearest core point is this PC, isn't it? So you add PB. You add PB. You add PB. Also this cluster now. That's how you add PB to this particular cluster. That's how we exactly handle border points. So we handled all these points. So first we labeled all the points as core points, border points, and noise points. We remove all the noise points. For each core point, we are just checking out what are the density connected points. To check for density connected points, we have to do range queries. Given this point, given point P, given point, tell me given point which are within which are within epsilon, which are within given point P, which tell me which are within epsilon distance, isn't it? I think this point P4, this point for P, which points are within P4, this point P4 and this point P1 are in epsilon distance. Again, if I say epsilon distance points for epsilon distance point for P1 and P4, they are for P1 and P4 are for P1 P2, for P4 is P5, isn't it? So range queries needs to be done even at this stage. Which stage? At this stage. You need range queries at this stage, not only in step 1, you need in step 3b also, when we have to determine density connected points to P. So the core operation is, so in step 1 it is range query, and also in step 3b it is again range queries, isn't it? So the core computation is range query, except that everything is mostly trivial. We remove noise points, we are handled all the core points. Then this is loop. This one, what is this? 3a 3b is loop. Each loop, when this loop 3a 3b terminates, each core point is assigned to at least one cluster. For border points, for border point, what is the concept for border point? We need step 4. We already discussed step 4. Just go to previous slide. This is for border point, isn't it? We are assigned to the nearest core points cluster. The most important operation is your range query. So range query is given a point xi, data set d, and radius epsilon. It returns all the points within a epsilon radius from xi from your data set d. Si equal to, what is my Si equal range query of xi comma d comma epsilon, isn't it? We will come to time complexity later, but using good data structures like KD tree, this can be done. This can be done using order of log n, where n is the size of your data set. Range queries can be computed within order of log n if n is size of your data set. We will come to the computational complexity a little later. Just go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.